playing that note, it would come through this door and it would be almost 90 degrees. It'd be like this. Okay? Now likely though, if you're sitting where Chris is sitting back there, right, you would still hear that tone. Why would you hear it? It's going to bounce. It's going to go in the room. It's going to bounce all around. But if this were an anechoic room, this would be approximately true, right? It would be like this. You couldn't see it, of course, but it would be like this, beam of light spreading out like this. And as he moved into that, approximately at that angle, he'd start to hear it, and it would get louder and louder. In fact, in the middle, it's loudest, et cetera, right? Okay. Say it again.
What kind of room?
Anechoic, one that doesn't allow echoes. Yeah. Not an anechoic room, not an echoic room. God help you if you're learning English, right? An echoic room, not echoic. An anechoic room, not an echoic room. It's a minute difference that matters by minutes, yeah. I just put radians, yeah. And then, what if we have a bass note? A bass note is like 40 hertz, right? So just for fun, let's toss 40 hertz in there for the frequency, right? Remember, we played 40 hertz in here. 40 hertz was this amazingly low frequency. So what's 343 divided by 40? How big is that wave? Is that 8.575 meters? Yeah, and that divided by 0.92 is what? That's 9.32 radians. Isn't that more radians than there are? Think about that. The sound comes out. I have a 40 hertz wave, has a wavelength of 8.75. When I figured this out, it's like 9.3 radians. What does that mean? A bass sound of 40 hertz coming through here, where does it go? Everywhere. It paints the walls, right? It goes, what's its radian spread? It's like all around. It's going all around, right? So that's why you can have like a tiny little opening like that subwoofer, and it'll still spread. It'll spread incredibly. The smaller the opening, the bigger it spreads out. Juliana's got a question. You figured it out, okay. That was strategic of me then to wait. Okay. Okay. Now, here is the final important principle, and this comes up over and over and over again. Okay. If you want to resolve something, basically your resolution, your ability to resolve things is on the order of the wavelength you use. If you're trying to make an image, it's like pixels on a screen. The more pixels you have, the smaller they are, the better the resolution, right? So the analogy that I'll make, and it's a good analogy, right? Suppose I were standing in that hall like this, and you were trying to determine what was in the hall by throwing objects of various sizes down the hall, kind of like dodgeball. Are you picturing this? Let's suppose you start off with beach balls. Beach balls are this big and they're inflatable, and you throw them down the hall. And all you can tell, by the way, is that there's something in the middle of the hall, on the bottom of the hall. You can get beach balls on either side of me and above me for quite a ways, right? And that's it. You don't know that I've got legs and arms and a head or neck or anything like that, much less that I have fingers, correct? Yes? So now let's up the ante. Let's use those red rubber bouncy balls. Yeah? Ouch. I'm standing there. You're hurling them down the hall. By a series of experiments, you now determine, and somebody, by the way, gets their PhD because of this, right? That this space at the bottom, that I've got this sort of, I'm narrower here, right? And that there's a space down here, and you can get, it's not solid. You can get a red rubber bouncy ball through that space. Yeah? Yeah? It's amazing, right? And then there's even a space here you can get a red rubber bouncy ball. So now I'm sort of taking on human shape, aren't I? Fingers have not yet been discovered, correct? The fine structure of the upper appendages is not yet, nobody's written that paper, right? Now you start using soft balls. Ouch. Right, now you discover like the neck. I do have a neck or something like that, right? This is further mapped out. Ouch, right? The width of the arm is measured to a high degree and all this stuff, right? Okay? Yeah? Now they start to use golf balls. Ouch. Right? Golf balls, somebody discovers the thumb with a golf ball. Right? It's like, whew, the golf ball fit through there. The fingers have not yet been discovered, right? Now I've got like paddle, like, yeah. Then you start using marbles. The finger is discovered. In fact, many fingers are discovered. Several PhD dissertations are written. I've discovered the index finger. There we go, right? And all this stuff, right? Then you start using, what do you use? BBs, metal BBs. Right? The structure of the fingers, yes, do we get the picture? Yeah? So if you think about it, like radar waves are on the order of meters long. Radar waves cannot then make an image. They cannot resolve things smaller than that. Light waves are on the order of like 700 nanometers, 400 nanometers. Okay? Atoms are on the order of, and that's like times 10 to the minus 7th meters, right? Atoms themselves are like 10 to the minus 10th meters. Okay? So you cannot, of course, resolve atoms with visible light, correct? Yeah? Visible light is too big to resolve something as small as an atom, right? So that's the concept here when we're talking about waves. So what do we do? If we need to really look at something close, what do we do? Can we not do this? Thanks. What do we do if we need to resolve something even smaller? Electron microscopes, which of course brings up the notion of what are electrons doing acting like waves? Well, they can act like waves, and they can act like smaller waves than light can, okay? So there's a concept for you, right? How about ultrasound? Why are they using super small frequency or high frequency sound for ultrasound? It's dangerous. It has high energy. It poses more of a hazard to fetuses and stuff like that, right? Why do they use that?
See if it's a boy or girl. Penetration.
Why couldn't we use 40 hertz? 40 hertz is totally safe. It's got a wavelength of 8.75 meters. We could tell whether there was a person standing in front of us, couldn't we? And that's about it, right? Maybe we could resolve a person. People are like 2 meters tall, right? Oh no, I guess we probably couldn't even get that, could we? Yeah? Yeah, so why don't we use 40 hertz? Too big a wavelength. Why are we using 100,000 hertz? Well, because that wavelength is really small, right? What's the wavelength of 100,000 hertz? Well, 343, it's sound, right? Let's assume it's going through air. It's not really, right? What is that? Well, divided by 1,000 is 0.343, right? So is that what it is? There we go, right? So you can resolve things on the order of 3 millimeters. Is that about the resolution of ultrasound images? Like something that big? Yeah, kind of. It's just not perfect, right? This is a very cool thing, okay? I watched an amniocentesis. Yes? I was going to faint because they like stick this big needle, right? And like, right? And then they have it on ultrasound to make sure they don't like stab the baby, right? I watched that going on. I did not watch the needle going in because I would have fainted, right? I watched, though, the ultrasound image, and the ultrasound glints off the needle. Isn't that crazy? It's like on the screen, it looks like a flash of light, only it's ultrasound. Isn't that wild? I just thought that was like, well, of course it would, but I hadn't thought about that, right? Radar waves, electron microscopes, right? This is why the sky is blue and sunsets are red. If you ever wonder why the sky is blue and sunsets are red, okay, during the day, what do we look at? Well, we look at the atmosphere, right? Yeah? And there are things in the upper atmosphere, okay, particles of dust that reflect blue light. Why doesn't it reflect, this is, by the way, an exaggeration of the atmosphere, why doesn't it reflect red light? Yeah, red light's too big. It doesn't bounce off it. It can't resolve it. It can't interact with it, right? So big wavelengths don't bounce well off of small objects, right? The object, it's got a wavelength, it's got to be the size of the object or smaller to bounce off it, right? So there's stuff up there. There's dust up in the upper atmosphere that reflects blue but does not reflect red, okay? So when we look up away from the sun's over here, what do we see? We should see blackness, but we see the light that's scattered by the atmosphere, which is what color? Blue. It's blue. The atmosphere scatters blue light, so when we look up, we see the atmosphere itself. We see the blue light scattered down, right? All this stuff is blue. Now, at sunset, what do we see? Well, now we're looking through the atmosphere, right? We're seeing what's left after it's gone through a lot of atmosphere. Isn't that right? At sunset, we look through the most atmosphere that we ever do, don't we? And so what's been removed by scattering from that light? What color? What color is being scattered out of that white light? Red doesn't scatter. It's too big. The blue scatters. It's small, right? So if you take the entirely white light and you remove blue from it, what does it look like? Do we know this? We don't know this. Color, light is all the colors of the rainbow, right? Red, orange, yellow, green, blue. indigo, violet. If you see all those colors at once, you see white light. Yes? Okay. If you take Roy out of it, what do you get? Jabib, right? Jabib, right? Looks blue. What if